Well, let's move on then. Accreting white dwarfs can do even more spectacular things. So let's talk about supernovae, cosmic explosions. This is an artist's conception. We don't see them like that. And first, let us discuss what kind of supernovae there are. There are just two basic types, and then there are many subtypes. I'll talk about this in a second. And phenomenologically, what happens is the star was some brightness, suddenly, over periods of days or weeks, becomes vastly brighter, reaching luminosity comparable to that one of the entire galaxy, and then slowly declines. Now, that's just tip of the iceberg, 1% or less of the total energy. Bulk of the energy generated in supernovae we can't see. It's in form of neutrinos, but we have detected them from one supernova, from the Magellanic Cloud. And then there is a kinetic energy that actually explodes the star, which is comparable to the amount of energy that's shown away in light. The expansion of the shell of the exploding star is some fraction of the speed of light, typically of the order of tens of thousands of kilometers per second, and slows down. And so what is left is one of those beautiful supernova remnant, plus a compact remnant in the middle, which is neutron star or a black hole, depending on the mass of the progenitor star. There is a new kind of supernovae called parent stability supernovae, which do not leave a remnant. We'll talk about them in a sec. So the basic classification of supernovae is type 1, type 2. And first, they were empirically classified on the basis of their spectra, whether or not they have lines of hydrogen in their spectrum. Hydrogen being by far the most common element, you expect it to be present. But type 1 supernovae have no hydrogen. And now we know why that is, because they come from white dwarf progenitors and their envelopes have been shed away. What was left is core composed of carbon, oxygen, maybe some helium. Type 2 do have hydrogen in their spectra. And a good rough number to remember is you get one supernova per galaxy per century, roughly speaking. Of course, depends on how many stars it's making and that kind of stuff, but this is a reasonable number. So in the historical times, in the Milky Way, we've seen three. There was the Crab supernova. There was the one seen by Tycho and one seen by Kepler. And we haven't seen others, but we know that there were others. They're just in hidden parts of the Milky Way, hidden by the dust. People found some of the radio remnants, which probably are supernovae exploded 1 or 2 centuries ago. But we can see them in other galaxies easily, and so to date, several thousand of supernovae have been found, more every day, literally, right? And we have a reasonably good understanding of the phenomenon. These two types correspond to two different mechanisms. Now, they have subtypes, which again depend on some variation of the spectral properties, and then they're one of a kind, and so on. And then there is this possible new type, well, they don't have a name yet, the parent stability supernovae, where the massive star is so massive, so dense and hot, that you create electron-positron pairs in its core, they annihilate and explode the star. So these are examples of supernova spectra, right? The one in the middle is so-called type 2, and you can see arrows are pointing to the Balmer lines. The one on the top is, well, and the others are not. They do not have hydrogen. They have all kinds of other stuff. You also notice that the lines are very broad. The reason for this is that there are high velocities involved. The supernova is expanding at speeds of thousands of kilometers per second, and therefore the lines will be broadened by comparable amount. If you look carefully, you see that many of the lines have this specific form that first there is an absorption and there is an emission. And that's called a P Cygni profile. The origin of this is that you have an expanding shell. The inner part is hot. Outer part is cooler. the emission from the inner part will be creating emission line, but then some of that will be absorbed by the cooler material in front, and so will remove some of the light from that emission line and turn it into absorption line. Those are called P Cygni profiles. They're also characteristic of sources where there is stellar wind or things like that. These spectra evolve in time. There are people who study this in great and gory detail and deduce the physics and nucleosynthesis that happens inside supernovae and so on. This is how light curves look like. The type 1a, used to be just type 1, but now there are subtypes, are supernovae with no hydrogen. They come from exploding white dwarfs. The type 2 are those that come from exploding massive stars at the end of their thermonuclear life. And they do differ in peak luminosities, in shapes. There is some variety. But always what happens is when you wait long enough, the light curve becomes exponential. This is log luminosity plotted versus linear time, so exponential is a straight line. This is a signature of radioactive decay. In the supernova explosion, sufficient energies and densities are created with enough flux of neutrons that you build elements heavier than iron. Some of those are unstable. In particular, those which have same atomic number as iron are produced in copious numbers, nickel and cobalt. They decay radioactively. The energy from their radioactive decay is absorbed by the expanding supernova remnant, converted into luminosity. So it's just if you were doing nuclear physics lab, if you plot Geiger counter rate versus time, if you do it logarithmically, you see a straight line. That's exactly the same thing. So let's talk about type 1a supernovae. Those are made by white dwarfs. What happens is that a white dwarf somehow acquires extra mass that pushes it over Chandrasekhar limit. Typically, this could be, it's in a binary with another star, and it keeps accreting and accreting. Once it goes above Chandrasekhar limit, the star can no longer sustain itself. Its core has to collapse. That releases enough energy to explode the star. Alternative mechanism that people talk about is that you have a white dwarf binary. You know, it used to be binary of two low-mass stars. Both end up as white dwarfs. White dwarfs orbit each other, but they lose energy because there are rising tides on each other. So that means they will spiral in slowly. Once they come close enough, they'll merge. So instead of 1 or 1.4 solar masses, you have twice that much. Same thing happens, the thing explodes. It's not clear at this point which of these two dominates, or both play in different ways and so on.